So in this problem, over the region R, there is a spatially uniform magnetic field. So this magnetic field is uniform, and at t equal to 0, the magnetic field is 1 Tesla, and it decreases at a constant rate in 30 seconds. So dB by dt is 1 Tesla divided by 30 seconds equal to 33.3 into 10 minus 3 Tesla per second. So that's the rate at which it's decreasing. What is the electric field in the region where R is less than R and R is greater than R? Okay, so let's do for R less than R. Now, okay, so here is the magnetic field. It's going into the sheet of the paper and it's decreasing. So the induced EMF should be such that EMF is such that it's wanting to oppose this change. So if it's decreasing into the sheet of paper, what you want is the induced EMF to produce a field into the sheet. And if you think about it, so the electric field will be in this direction, so it would drive a current in that direction, and a current flowing in this direction would produce a magnetic field into the plane of the paper. So that's what we need. So the line integral of the electric field around the closed loop is equal to minus d by dt of b dot area. Okay, b dot dA. It's an integral, but anyway. So E times, and this is R less than R less than capital R. Okay, E times 2 pi R equal to well, now we'll do the absolute value. So d by dt of b times pi r squared, and E times 2 pi r equal to pi r squared d by dt. Okay, so the pi cancels, one of the r cancels, so the electric field is 1/2 r dB by dt, and dB by dt is 33.3 times 10 minus 3 Tesla. So the induced electric field is 1/2 R times 33.3 times 10 minus 3 10 minus 3, and since this is electric field, it will work out in volts per meter. And let me clean this up. So 16.65 volt per meter. Okay, so that's the electric field inside. For R greater than R, we would draw a circle like that, and that's the radius. So again, E dot ds should equal minus del by del t of b dot dA. Okay, so this for r greater than r, oops, this is again E times 2 pi r, except that now the flux is only in pi r squared. That's a constant. And so E is one of the pi's cancels, and it's r squared over 2r and del by del t of b. So which is 33.3 into 10 minus 3 r squared over 2r into little r. And so you can see that the electric field is falling off as 1 over r outside the region. Okay, and inside the region it increases with r. Okay. So okay, let's see what else do they want. B, assume that r is 10 centimeters. How much work is done by the electric field on a proton that is carried once clockwise around a circular path of radius 5 centimeters? Okay, so for B, oops, you're going to take a proton around 5 centimeters around this path clockwise. Okay, remember the electric field was in this direction, so the work done is positive. Okay, let's look up the expression for the electric field. The electric field is equal to 16.65 to 10 minus 3 volt per meter, and the work done okay, so the work done is force, work done is force times distance. Force is the distance traveled is this distance traveled is the circumference of the circle, is force is q times E, and 2 pi r is the distance, and the charge of a proton is that many coulombs. The electric field is there's an r 16.65 into 10 minus 3, and r is 5 centimeters, 5 into 10 minus 2 meters volt per meter. Into 2 pi into 5 into 10 minus 2 meters. And the work done is equal to 10 to the minus 19, 10 to the minus 22, and minus 26. Okay. And since it's work done, that will work out in joules. 1.6 into 16.65 into 5. All right, so into 2 pi into 5 into, what was the power of 10 again? 10 minus 19 minus 22 minus 26 joules. Okay, so this is equal to 41.8 into 10 minus 24 joules. So that's the work done. All right, so what is the next part? How much work is done by the electric field on a proton that's carried once counterclockwise around the circular loop path of any radius r greater than. Okay. So this is part C. And so part C. So R is greater than R, and the work done, and you're moving counterclockwise. So you're traveling counterclockwise. The electric field is in this direction, and the electric field for R greater than R is, as we saw, it falls off as 1 over R. Where is the expression? Okay, so there is the expression for R greater than R. Here is the expression 16.65. R squared by R. Okay, so R, little r is greater than R. And what is it that we're trying to find? How much work is done by the electric field on a proton that's carried around once counterclockwise around a circular path of any radius at the instant when B is 0.5 Tesla. Okay, we'll come to part D in a second. Okay, so the work done will be negative since you're going around. ds is counterclockwise and electric field is clockwise. So okay, so the work done is minus 2 pi r times the electric field, and the electric field is 16.65 into 10 minus 3 volts per meter. No, that's Tesla per second. Okay, it's R square. So this is not dependent on R square. Okay, now we can put in all these values. Negative 2 point, and R is 10 centimeters. Okay, so let's and this works out too. So let's take care of powers of 10, 10 to the minus 7, 10 to the 5. Okay, so 10 to the minus 5. Oh, I forgot to multiply by the charge. Times the force is Q times E. So the charge of the proton. There's a Q here, Q here, Q here. Okay, so minus 2 pi 16.65, and what did we say? 10 minus 3, 10 minus 7, 10 minus 5, Q into 10 minus 5. And this will work out in joules. Minus 2 pi 16.65. Q is 1.6 into 10 minus 19 into 10 minus 5 joules. Okay, so that's 10 minus 24. So this works out to minus 167.4 into 10 minus 24 joules. That's the work done. Okay, part D is at the instant when B is 0.5 Tesla, proton enters the magnetic field at A, moving at a velocity 5 times 10 to the 6 meters per second, or the electric and magnetic forces in the proton at that instant. Okay, I won't do the numbers, I'll just set it up, and this problem is a little too complicated for it to be on the exam, so you don't have to worry about that. So the magnetic field is into the sheet, the velocity is like that. The magnetic force, according to the right hand screw rule, is as you turn from V to B into the sheet, the magnetic force will be in that direction. The electric field is like that, so the electric force will also be in that direction. So the net force will be the force due to the electric field will be also in that direction. FB plus FE, and this is QVB plus QE. So QVB plus E. And since R equal to R, we can use this expression for the electric field. And R is 10 centimeters. So this okay, I think we'll end right there so you guys can put in the numbers. So this is a long